All right, so you saw that if you attach a mass to a spring, and this is the equilibrium position of the mass, okay, if you pull this mass away from the equilibrium position, the restoring force is equal to minus kx, okay? That is, the restoring force is proportional to the displacement from the equilibrium position, okay? So the further out you pull it, the stronger the spring pulls back, okay? K is the spring constant, okay? Stiffer the spring, bigger this number is. And if you let go of this, if this is frictionless, this thing will oscillate like that forever, okay? The time for one oscillation is the period, and in a later chapter you'll study the period is 1 over 2 pi divided by m divided by k. Greater the mass of the object, longer it takes to complete a period for a given spring, okay? Anyway, the important thing I want you to notice is this force, it's called a restoring force because it's bringing you back to the equilibrium position. The restoring force is proportional to the displacement, okay? And this is called Hooke's law. All right, and this is the kind of motion that you see, and this motion is very important. We will dedicate an entire chapter to this motion. This motion is called simple harmonic motion. So here we go. So here's the mass attached to a spring, and there's the motion. Okay, spring strength, okay. And if there is no friction, this will keep oscillating forever, okay. And one oscillation is here to there and then back, okay. And I gave you the formula for the period, okay. All right, well, why are we talking about this in the middle of gravity? Well, here's why we're talking about it, okay. So now let's look at this picture. Let's say you had a shell. So for instance, this could be a basketball and you found yourself inside the basketball. Okay, what Mr. Newton proved is the following. Okay, if that was you, this piece of the basketball attracts you in this direction, and this piece of the basketball attracts you in that direction. Okay, you see this piece is bigger than that piece, okay, and the force of gravity is given by, the magnitude of the force of gravity is given by g m m1 m2 divided by r square. This piece is bigger, but it's further away. And so this was a theorem Mr. Newton proved, and it wasn't easy. These two forces exactly cancel each other. So that's what Mr. Newton proved. No matter where you are. So what does that mean for the inside the shell? What is the force of gravity on you? Zero. Very good. Okay, that's what Mr. Newton proved. Okay. So again, this has to be radially symmetric and so on. Okay. Yep.
So then that would mean that the atmosphere doesn't exert gravity on us.
Very good. Very good. Right. Very good. Okay. In fact, let's give him a hand on that one. Good observation. All right. So what that also means is, let's say here's the Earth, and let's say for some reason you dug a hole and there you are. Why is it doing that? Why is it doing that? Crazy. All right. So let's say you're here. So that means this portion of the earth doesn't attract you. Only this portion of the earth is attracting you. Okay? So if you extend that, if you find yourself at the center of the earth, the force of gravity on you is 0. Okay? So the shell outside doesn't attract you, only the mass inside attracts you. And so if you find yourself at the center of the earth, the force on you is 0. All right, so let's see what does all that mean. Okay, so by the way, so the Earth's radius is 4,000 miles, and the deepest hole we've dug is 4 miles. So 1 part in 1,000. We barely scratched the surface. Okay. Keeping that in mind, let's say you dug a tunnel through the Earth, and the tunnel passed through the center of the Earth. Here's what the force on you would look like. Okay. This constant. Okay. So this is your mass. G is the acceleration. G is the universal gravitational constant. That's the density of the Earth, and this is assuming a uniform density, okay, which is not true as well. But you see, the force on you is pulling toward the center, and it's proportional to the distance from the center. It's exactly like that mass attached to a spring. It's exactly like this, with the spring constant being that. Okay, that's the force on you. So what would happen? Let's say you dug a tunnel through like this, and you stepped into the tunnel. What would happen is you would oscillate back and forth, just like that mass. All right. So now I'll tell you something amazing about this. The period of oscillation, okay? The period of oscillation is given by this formula, and it turns out to be 85 minutes. Okay, do you guys know how long it takes for the space shuttle to go around or the International Space Station to go around the Earth? 90 minutes, 85 minutes. It is crazy.
You'd be going so fast by the time you get to the center.
I'm sorry?
By the time,
Okay, so,
jump in
okay,
pretty fast.
do you guys know how,
The middle.
do you know how fast the space station is going around the Earth? About 18,000 miles an hour. That's the speed. If you fall into the tunnel, when you're going at the center, your speed is 18,000 miles an hour. Exactly the same speed as that. So again, and when we get to chapter 15 or so, you'll see that these motions are related. Okay, this is a simple harmonic motion. And uniform circular motion is a combination of two simple harmonic motions. All right. So, in fact, I'll look this up just before coming to class. Shanghai and Buenos Aires are antipodal points. So, you can step into this tunnel in Shanghai and be in Buenos Aires for lunch in 45 minutes. Okay. And then after your lunch, step back and you can come back there. All right, what this graph shows you is the following. Of course, the density of the Earth is not uniform. But if the density of the Earth were uniform, this is how the gravitational acceleration due to gravity would look like. On the surface, what is the acceleration due to gravity? 9.8 meters per second squared. Okay? And as you go further, you see the radius of the Earth is 6,400 kilometers, and if you go around 13,000 kilometers, it would be 2.5 meters per second squared. And if the density were uniform, the acceleration due to gravity would linearly decrease and go to 0 at the center. But in fact, the density is not uniform. This stuff is much more denser than this stuff. Okay? And you see the actual acceleration due to gravity is the highest around 3,500 kilometers. at a distance of 3,500 kilometers from the center of the Earth, about halfway. And there it's 11 meters per second squared. Mhm. Okay, do you guys remember the formula for gravitational potential energy? mgy, very good. Yeah. And y was the distance above the ground. Okay. So when is this formula good?
Gravity is constant.
When this is constant. Very good, my friend. So when this is constant. And I just showed you a graph where g is not constant. You see here, g is decreasing. But for g to decrease sizably or noticeably, you have to go quite far. You see, this is almost 1,500 kilometers. That's 1,000 miles. You have to go 1,000 miles before it is noticeably different. Okay, but nowadays we go far off routinely, or at least objects go far out routinely. Okay. So we need a more accurate expression for the acceleration due to, for the potential energy, gravitational potential energy. And this is the more accurate expression. This is the correct expression. What this is, so the gravitational potential energy is negative g, the mass of the central object, and your mass divided by the distance, your distance from the center of the Earth. Okay? And the way to derive that is the following. How many of you guys have done spherical polar coordinates? How many of you know spherical polar coordinates? Okay. All right. Well, I was going to show you the derivation, but maybe not. There's too much other good stuff to do. Okay. Or do you want to see a derivation of that? All right, I'll sort of give you an introduction to spherical polar coordinates. And by the way, when you are in the mathematics department, they do it slightly differently. Physicists do it slightly differently, okay? So here's a point, and its coordinates are x, y, and z. Yeah. So there's that point, okay? Now, let's draw the shadow of that. Yeah. So what are these coordinates? That they give you the address of this point. Okay. So you need 3 numbers to get the address of that point. Okay. Now these 3 numbers are not unique. You can do other numbers to give you the address of that point. Okay, so the spherical polar coordinates, r is this distance, theta, so this is what the physicists do. Theta is the angle of this vector from the z-axis, and phi is this angle. Okay, so we can give you the address of that point as r, theta, phi. These are spherical polar coordinates. Okay. All right. So in this, these are called Cartesian coordinates. Okay. So a small, again, this is something that you'll learn in Calc 3. Okay, I believe that's where you learn about it. So I'm just, so a small displacement, dr, so this is a small displacement, dr. You can write that displacement in terms of these coordinates, or in terms of these coordinates, or any coordinates that you choose. Why do you have different coordinate systems?
Different applications.
Different, when you have different problems, if you have a problem that has spherical symmetry, then these are the coordinates that you want to use. Okay, so for instance, if you're solving a problem that has spherical symmetry, meaning like a basketball or the earth and stuff like that, then these are the more convenient coordinates. It's like, if you go to South America, you don't want to be talking English or stuff like that. So if you can talk Spanish, your life would be much easier. Okay, so that's the deal. Okay, so this small displacement in terms of Cartesian coordinates is written like so. Well, what does this mean? You went this distance in the x direction, plus then you went this distance in the y direction, plus this distance in the z direction. Okay, that's what that means. So just like to get to this point, you went x distance in this direction, then y distance in that direction, and then z distance in that direction to get to that point. Okay, just like that. For this small displacement, this is the small displacement in the x direction, small displacement in the y direction, small displacement in the z direction. Okay. Of course, you can write this in terms of polar coordinates, spherical polar coordinates. So dr can also be written as dr r hat. Okay, what was I? I forget, what was I?
Vector for x.
Unit vector in the x direction. What was J?
Y.
Unit vector in the y direction, and K was, yeah, K was the unit vector in the z direction. Okay. So again, you gave a small displacement as the sum of this displacement plus this displacement plus this displacement. So similarly, again, I'm just going to do 30 more seconds of this because, all right, so r d theta theta hat plus r sine theta d phi phi hat. Okay, it turns out that, okay, so this is a unit vector in the radial direction. Theta hat is a unit vector in this direction. As theta increases, it's tangent to that circle. And phi is a unit vector, this tangent to this circle in that direction. All right, so that displacement is given in terms of those unit vectors. The gravitational force is given by Gm r hat. Okay, and in that integral, in the line integral, what you have to do is dot dr, and you have to integrate that. And so it's integral of minus Gmm r square r hat dotted with dr, and that's equal to, again, don't worry about this. This is, like I said, you'll see this in Calc 3, and I shouldn't have gotten into this, but now I'm knee deep, so let's. Okay, and now you see, when you do the dot product, r hat, that's the only one that survives. Like I dot I, r dot theta dot dies because they're perpendicular to each other. R dot phi dot dies. Okay, so this line integral is equal to minus Gmm by r squared dr. Okay, and this integral is very easy to do. It's Gmm by r. minus 1. Yeah. Okay. And then you can apply R initial to R final. Limits R initial to R final. Okay. And that's what's done here. Okay. So the limit is R initial to R final. There it is. But the work done is, so that's the line integral. It's negative of the potential energy. So there's the potential energy. That's how you get that. That's the more accurate, that's the correct expression for the potential energy. Except that unless you're jumping 1,000 miles, you don't need to use this because this is a pain in the neck to use. It's a very bad pain in the neck. Okay, my friend, what's your question?
Oh.
Yeah.
Why so for example, d theta
Mm-hmm.
was r times d theta.
Mm-hmm.
And for d phi,
Mm-hmm.
it was r sine theta d phi. Why is there a
So
sine
this is costing you a good story, brother. I mean, if you spend time on this, okay, so r d theta is this distance, d,
Yes.
okay? So that's the distance you're traveling parallel to this, in this direction when the angle increases by d theta. Okay, so let me draw that. This is d theta, and this distance is r d theta. Okay, and this is r sine theta. This, which is this distance, is r sine theta, and then this would be d phi. So that distance would be this distance. R sine theta is the projection. That's the distance of the projection times. So r sine theta is that times d phi is the distance along the phi hat direction. Okay. All right. So the point of all that long story was, now we have graduated from this expression to this expression. See, we are friends with Elon Musk, so this is not good enough anymore. We want this expression. Okay? But again, if you can get away with this thing, that's what you're going to use. When can you get away with this thing? Yeah, as long as you're not jumping 100 miles or more than 100 miles, this is good. You jump 1,000 miles, this is what you need. Okay? All right. So let's say you're playing with the solar system and you want to know the gravitational potential energy of this system. The gravitational potential energy of this system is the potential energy of this pair plus the potential energy of this pair plus the potential energy of this pair. Okay? And that's what this is. The potential energy of all the pairs. Okay? So if you have n particles, how many independent pairs do you have? N times n minus 1 divided by 2. Okay? So if you have 3 particles, 3 times 2 is 6, 6 divided by 2 is 3. 3 independent pairs. Okay? Okay, what does this mean? Escape velocity.
The speed you need to be to break free
I'm sorry?
the speed you need to be in order to break free from the gravity.
Right. So the question is the following. Let's say I throw a tennis ball, it goes a certain height and then comes back. I throw it faster, it goes higher and then comes back. Can I throw it such a speed that it will never come back? Again? And that is the escape velocity. And it turns out that there is such an escape velocity. Okay? So from the Earth, from the surface of the Earth, if you throw an object at 11 kilometers a second, 11.2 kilometers a second, it'll never come back. Now here's the deal with that speed. You can throw it straight up this way. So in any direction about these lines, okay, and it'll never come back. Of course, if you throw it straight at Earth, then all bets are off. All right, so that's the escape velocity. You also understand that, so from the surface of the Earth, you have to throw it 11 kilometers a second. How about here? If I'm this far away, you don't have to throw it as fast. Okay? So the further out you are, the slower your escape velocity from the same object. Okay? Well, why do you care about this kind of stuff?
For things like space travel.
Yeah, so if you want to, go far, far away, you're escaping the Earth's gravity and so on. Do you guys remember the speed of the International Space Station? Very good. Who said that? So it's 8 kilometers a second. 8 kilometers a second is less than 11 kilometers a second. So that's why it's not escaping. Okay? So it's bound to Earth. All right. So the escape velocity from an object, there's the central mass, and this is from the surface. International Space Station is very close to the surface, so you can just put that. Okay, the International Space Station is only about 250 miles from the surface of the Earth. Okay, is that? Okay, so the escape velocity from here, and you can put in the numbers, and it comes out to be 11.2 kilometers a second. Now, here's a very interesting fact. What is the fastest you could travel? Speed of light. Okay, so you see, if you start reducing this radius, what that means is you take this object and try and squeeze it and make it smaller and smaller. As you reduce this, the escape velocity is increasing. Okay, what if you reduce it to a size such that the escape velocity becomes the speed of light?
You can't escape.
So here's the object. You've reduced it to such a small size where the escape velocity from this radius becomes the speed of light. You've turned this object into a black hole. That's when the object becomes a black hole. Okay, so if you want to turn the Earth into a black hole, you got to squeeze it into the size of a marble. Yeah. If you want to turn the Sun into a black hole, you have to squeeze it to the size of about 3-kilometer radius. Okay. All right, so that's what a black hole is. And of course, if you squeeze it to that size, then it won't stop. Einstein says all that matter would just fall into the center, into a point, to a singularity. Okay. So, escape velocity from distance r from a planet of mass m is given by that. Here are all the escape velocities from the surface of various objects. So from the Earth, it's 11.2 kilometers per second. Okay. From Jupiter, it's 60 kilometers per second. Okay. From the Moon, it's 2.3 kilometers per second. Okay. What is in our atmosphere? What is our atmosphere? Our atmosphere is 78% nitrogen and 21% oxygen, okay? And less than 1% of other stuff. Okay. We don't have any helium in, so %98 of the molecules in the universe are hydrogen. No, 92%. And 8% are helium. We have none of that in our atmosphere. So where did that go?
Into the sun.
What's that?
Into the sun.
It all escaped. Okay, so the atmosphere of a planet depends on the escape velocity and the temperature of the planet. So the temperature, our temperature is about 14 degrees Celsius. At that temperature, all these molecules move so fast that they would escape. Okay, only the heavy stuff stays back. That's why the moon doesn't have any atmosphere. The escape velocity is low, and given the fact the proximity to the sun, it has no atmosphere. Our moon could have had an atmosphere if it was maybe near Pluto's orbit. Okay. So the atmospheric composition of a planet is determined by the escape speed and the average atmospheric temperature. Okay. So like I said, today's speaker will talk about the atmospheres of exoplanets and some dead stars. Yeah. If the average velocity of a gas molecule is 1/6 the escape speed, then the gas will not be present on the planet. So here's the escape velocity. 1/6 of that is about 2 kilometers, a little less than 2 kilometers a second. So if you go to Publix, buy a helium balloon, release that helium in the atmosphere, the average velocity of those helium molecules is greater than 2 kilometers a second, and they'll all escape. So what happens is first the fast molecules escape, and then these get speed up and so on. Okay, here's the sun, and there's a planet going around the sun. Okay, the force of gravity is Gmm by r squared. So the magnitude of this force is given by m is the mass of divided by r squared. Okay, so what this is saying is the orbit around this mass has only one of these possible shapes. It can be a circular orbit, an elliptical orbit. Okay, so these are bound orbits. These are bound orbits, meaning it's bound to the sun. This will keep orbiting forever as long as there's no friction. Okay, so if the force is an inverse square law, the orbits are one of these guys. A parabola, so a parabola is an unbounded orbit. A parabola or a hyperbola. A hyperbola is, okay. So for these orbits, the energy is less than zero. For this orbit, the energy of this object, total energy, is zero. And for this orbit, the energy is greater than zero. Okay, so that's the classification of orbits. Yeah. You'll get an orbit like this if you go far, far away and take a tennis ball and drop it towards the Earth. Yeah, of course, you have to miss the Earth, and it'll go on a parabolic orbit. So it'll go infinitely far away and then stop. If you want an orbit like that, you have to throw the tennis ball at Earth. Okay? All planets, of course, go in elliptical orbit around the sun. Okay? So the energy is the kinetic energy of the planet plus the potential energy of the planet. Okay? So if this energy is less than zero, bound orbit, then it's a bound orbit. Mr. Kepler gave us 3 laws of that planetary motion around the sun seem to obey, or they obey. Okay. And Mr. Kepler gave us these laws before Newton came up with his law of gravity. Okay. So he said, before we knew about this law. Okay. So he said all planets move in elliptical orbits with the sun at the focal point. So all planets move in elliptical orbits. And now we know that if you have a law like this, all planets go either in circular orbit and elliptical orbits. Okay, and that's a random thing. And, if you're randomly choosing a closed orbit, what are you going to hit? Are you going to hit a circular orbit or an elliptical orbit? Elliptical. There's a higher probability of being in an elliptical orbit. Okay, so all planets end up are going in an elliptical orbit. The second law says, okay, so this is the planet now. Yes, oops. Okay, so the second law says here's a planet now, and let's say in 1 month it went from here to there. So this is the area it swept out. This is the area that it swept out. Okay, and then in another month it went there. This area will be equal to this area. Okay, so the area it sweeps out in equal time intervals are equal. Okay, so let me show you another picture. Okay, so let's say this planet went from here to there in a week or in a month. It went from here to here in a month. It went from here to here in a month. All these areas are equal. Okay, so that's, Mr. Kepler said that's the second law. So the radius vector drawn from the sun to a planet sweeps out equal area in equal time intervals. Okay. And the third law says square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Okay. So let's say, I'll simplify this third law for us. Let's say r is the radius of the orbit. What Mr. Kepler said is t square. T is the period for the planet to go around the sun, divided by r cubed. R is the radius, orbital radius of the planet, is equal to, is constant. Yeah. It's the same constant for all planets. So we have 9 planets, okay? And you can take the period for each planet and the orbital radius for each planet, calculate this ratio, and you get the same number. So here are all the objects: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. So for all these planets, you see t squared by r cubed is the same number. Yep. So those are the 3 laws, Kepler's 3 laws for planetary motion. Okay, well, so by the way, so what, today we know this, Kepler didn't know this, but for an inverse square law, if the force is like this, what are the orbits? The orbits are elliptical. That's a closed orbit. Okay. And so the Earth goes around in an ellipse. It's been going around in the same ellipse for the past 5 billion years. And it'll keep doing that for another 5 billion years, till the sun swallows us. Okay? So if that is the force, okay? So look at this. This is Mercury's orbit. It's not a closed elliptical orbit. See, the orbit is precessing. So what does that mean? What's that?
That the laws aren't perfect?
That means this is not the correct law, the force law. If it's an inverse square law, then that's a theorem. So if you found an orbit that's not closed like that, that means there must be some correction to this term. Okay, so Newton's law of gravity is an approximation. The next better thing is Einstein's general relativity. Okay, but from here to go from here to there, what was it, 1700? It was about 250 years. Okay, so that progress didn't happen just overnight. All right, so when Einstein came up with his general relativity, that's the first calculation he did. And that's an amazing story in itself. This measurement is an amazing story. Okay. Kepler's second law, which says that this vector sweeps out equal areas in equal time intervals. So that's what this is, the rate at which the area is swept out, and I'm not going to go over the proof. The fact that this is constant is really a reflection of the fact that the angular momentum is constant. Okay? The angular momentum of this planet is constant. Now you saw that Newton's second law says the torque acting on a planet or an object is equal to rate of change of angular momentum. So if the angular momentum is constant, this is zero, that means the torque on that planet must be zero. Okay? Well, the only force acting on this planet is the gravitational force, which is going right through the center, and so the torque of this force is zero. The torque is zero, and so the angular momentum is zero. Rate of change of angular momentum is zero. Is a consequence of conservation of angular momentum. Gravitational force has zero torque, so angular momentum is conserved. Okay, but Mr. Kepler didn't know all of this. Okay. So again, here's Newton's second law. The modern way of saying it is angular momentum of an orbiting planet is constant. Okay, here's Kepler's third law. Okay, so like we said, the period of this object going around this mass, central mass, divided by its period square divided by its radius cube is a constant, and it's related to the mass of the central object. Okay. So you can take any object, you can measure its period, and if you can measure its orbital radius, then you can get the mass of the central object. Very neat. All right, you want to go home and calculate the mass of the Earth? So what is the period for this space station? I'm sorry? Yeah, 90 minutes, 85 minutes. What is its orbital radius? It's the radius of the Earth essentially. So 6,700 kilometers, or 6,000, let's say 6,800 kilometers. So put those numbers and you can calculate the mass of the Earth. Okay. You guys know that here's a galaxy, and at the center of most galaxies, there are massive black holes. How do we know the mass of these black holes? You do this, you look for a star close to the center, and it's going at crazy speed. You measure the period of this, or the orbital period of this star, and the orbital radius, and you can get the mass of this central black hole. Yeah. So let's see. See, that's what this is. Okay. So this is at the center of some galaxy. They measure the orbital period of these stars. They're all going around a massive black hole. Okay? And that's how they get the mass of these central black holes. Okay. So again, also you could get the mass of the sun. You can get the mass of the sun. The Earth goes around the sun once in 365 days. This distance is 92 million miles, so you can put those numbers in and get the mass of the sun. So if you can get the mass of any central object as long as you know the parameters, orbital parameters for this body that's going around the central object. Okay? So the mass of the sun, put the orbital radius of the Earth, orbital period of the Earth, and you can get the mass of the sun. Okay. Again, remember this constant was measured in 1800, and soon as that constant was measured, you got the masses of a whole bunch of objects, astronomical objects. Okay. Here's a satellite going around the Earth. The orbital speed of the satellite is given by this formula. R is the distance from the center of the Earth. Okay. A geosynchronous satellite is, do you guys know what a geosynchronous satellite is?
In order to the same speed the Earth is rotating.
Yeah. So, well, that is true, but there needs to be other things that need to be true. Okay, so here's the North Pole, here's the South Pole. So again, the radius of the Earth is 6,400 kilometers. So if you're 36,000 kilometers above the surface of the Earth, so I can't draw it to scale here, but okay, if you're 36,000 kilometers above the surface of the Earth, so the orbital radius is 42,000 kilometers, okay, roughly. And then your orbital period is 24 hours. Okay. So now this orbit can be in any direction as long as you're in this, that's your orbital radius. Okay, so if you're going like this, you're taking 24 hours, but then that's not a geosynchronous orbit. Okay, so if the Earth is rotating like this, you have to go above the equator, you have to be right above the equator, and be going in the same direction as the Earth spinning, and then you'll be about the same spot on the Earth. Okay, if you're going in the opposite direction, you won't. Okay. So you have to be right above the equator and going at taking 24 hours, and that is a geosynchronous orbit. Okay, and you saw that that's a very desirable orbit because you can park your satellite there and use that for signals, okay, for TV signals and all. So the orbital speed in a geosynchronous orbit is 3 kilometers a second. Okay, so this is the total energy of a satellite. It's kinetic energy plus potential energy. And since the satellite is going around the Earth, it's bound to Earth, it's not going away anywhere. And so the total energy is less than zero. Yeah. So for bound orbits, the total energy is less than zero. So if you want this guy to escape, his energy needs to be greater than zero. You know? And it turns out that for a circular orbit, there's the total energy. The kinetic energy plus the kinetic energy turns out to be half the potential energy. Okay? And there's the total energy. This is the total energy for an elliptical orbit. Today there are about 12,000 satellites going around the Earth, active satellites. I just looked it up. There's over close to 130 million pieces of object greater than 1 millimeter in size. Yeah. These are the geosynchronous orbits. These are the geosynchronous satellites. Okay. This is all low Earth orbit. Okay. Satellites. Okay. All right.